So if you do the thing, what we learned there is, whenever we had a binary code or the systematic, it was low complex. And the reason for this was that we had this number of zeros there that helped us to somehow clean up the matrix, and the number of operations on the decoder side was so little. Now, that came to another idea. Why don't we put zeros into the matrix anyway? I think I made this example with Sudoku. It's like giving you one more number and say this is a 5 and this is a 7, and then it becomes easier and easier to solve it. That's more or less the same way here. So if the zeros are really the point, why don't we add more zeros there? A binary code has 50% zeros in there anyway. The deterministic depends a little bit on the loss rate, so they were quite good. And if it's random, just imagine we fill it up randomly and then we add a little bit more zeros. Who can say whether it was random or it was us? The question is, how many zeros should we add there? And why don't we fill up everything with zeros? Right? That's the easiest way, but then we will never transmit anything. So the point is now where to transmit this, where to put the zeros in order to reduce the complexity. So here, every time it gets more and more and more. And these are some measurements that we did on the phone. This was Xperia phone at the time that we used for this stuff. And you see here on the y-axis the decoder processing speed, megabyte per second, over the mean number of non-zero coefficients. So what it does mean, we have a generation of 32, 256, 2000. So let's take the blue one, right? So at this point on the right, on the outer point, what you see is that 32 packets were non-zero. So this is the full RLNC. And then we added a little bit of zeros. And did it help? Yeah, marginal, right? So only when you go really deep, when there are only 4 non-zero elements, the coding speed, the processing speed goes up. The same for other generations. Before that, putting a little bit of zeros does not help so much, right? And you see, then you have to go up to this point, and here you go up later. As you have more generation, the coding speed goes down, but with sparsity, you go up, right? Now, what you can see is the less dense it is, here for the blue one, you have 20 megabyte per second, and you can bring it up to 30 megabyte per second. 300 megabyte per second, sorry. And here you had 0.4 megabyte per second, and you go up to 33 megabyte per second. So this is 1 order, 2 order of magnitudes that you get by putting this sparsity. So great. What is the risk of putting zeros there? Even if it don't, yeah?
You might get packets that you already know. So because there's a higher chance that you don't get something independent from what you received before.
That's correct. So what we say normally is you have seen the packet in a way that the rank is not increased, so it's linear dependent, right? So this is a little bit the problem, and therefore the question is now, how many zeros we would like to put in, and what is this? We would like to reduce the complexity, but we don't want to risk the other one. Of course, there's a trade-off. And here there were some results, and this was for the binary field. In the binary field, you're somewhere in the middle, right? The number of coded packets received to decode, right? So let's just talk about the red line here, the mean, right? So if you have already 50% zeros in there. So if you create too many ones or zeros in one or the other end, then you see you have to send more packets because you increase the linear dependency. So even adding more ones, so reducing the number of zeros, what you will see is the dependency goes up. So what is if it's not binary, right?